the screen?
Yes, sir.
Thank you. So we have defined a branch of logarithm in the previous class. So what was that? That was precisely if you have a function from a region. So this is a region. Complex valued function which is continuous and satisfies e to the f z is equal to z for all z. Okay, so this is what is called a branch of the logarithm. Okay, this is a branch of logarithm. So that is how we have defined it. We have seen one particular example, namely the principal logarithm. Okay, and we have seen that. So this is well defined. If we remove this half line, so this is a region itself. You can choose this to be your G. And we have seen yesterday that this is the maximal region on which this function is a branch of logarithm. Okay. Now the point is that if we have the principal logarithm, we can get other values of log z in terms of the principal logarithm in this way, right? We have seen that this is precisely log z plus 2k pi I, where k is an integer, right? Which is precisely, we know, the real logarithm plus principal argument plus 2k pi. So we know this. Now the point is that if you choose any integer k, okay, if k is equal to 0, we have the principal logarithm, which is a branch of logarithm according to the definition. It satisfies both. It is a continuous function, it is well defined, single valued, and it satisfies this equation e to the fz equal to z. Now the point is that for any k, what can you say about this function if you call it fk of z to be equal to, say, log z plus 2k pi I, okay? Then what can you say about this function? So we have seen that this portion, this is well defined on c minus this. If you successfully remove the negative half of the x-axis, so this is well defined here, and this is just a constant. So this function is well defined. This function is well defined from right. So this is defined, well defined, okay, and continuous. You agree with this? Why continuous? Because this portion is continuous and this is just a constant. So it is continuous. And since this function has discontinuity on this half of this line, so does fk for every k, right? This fk has also discontinuities on this particular half of negative x-axis. So for each k belongs to z, this fkz, if you define it this way, okay, this is a well-defined single-valued function. This is well-defined single-valued, and this is continuous. Now, if you just see, if you just test, so it satisfies the first criteria. I am going to show that this is also a branch of logarithm. So it satisfies the first criteria. It is well-defined and it is continuous on this region, and into the fkz, that is also z, right? Okay. So this is e to the log z times e to the 2k pi I, which is equal to z. So therefore, this fkz from c minus is a branch of logarithm for every k. Okay. So this is clear. So if we have one branch of logarithm, we have infinitely many branches of logarithm in the same region. Mind it, in the same region. We are not changing the region. Okay. So this is indeed true for any branch of logarithm anywhere. Okay. We are going to state this in general. This is a particular example we have seen. We have the principal branch of logarithm, and we have, in terms of the principal branch, we have all other branches of the logarithm, for every k, okay, in the same region. My point is, this is indeed true for any region and any branch of logarithm defined in that region. How? Let us see. Let a from G to C be a branch of logarithm. Then another function G from G to C is a branch of logarithm if and only if this gz is equal to fz plus 2k pi I for some So you just look at the statement of this theorem. If we have one branch of logarithm f defined on a region G, then what are all the branches of logarithm? They are nothing but that branch of logarithm plus 2k pi I. So in this way, we obtain all possible branches of logarithm in a region. If you have one branch of logarithm, you have all branches of logarithm in that region. That's what this theorem tells us. This is if and only if. Okay. So the proof is, I would say, very easy in a similar fashion. So if G is of this form, then there is nothing to prove. Or some K, then we have this, right? Number one, G is continuous. Why? as f is continuous, right? So it has to satisfy both the conditions. And number two, e to the gz is equal to e to the fz plus 2k pi I, which is e to the fz times this portion is 1 and this portion is equal to z, so it is equal to z. And this happens for all z in G. Therefore, it is simple. G is a branch of logarithm. Okay. Now, what about the converse part? How do you show the converse? So let you have a branch
Sir,
of logarithm.
hello, sir.
Yes.
In the statement, it is for some k in z, or for all k in z in the statement of theorem.
So you just look at the statement of the theorem. You just look at the statement of the theorem.
Yes, sir. It is in the last. It is for some k in z.
The statement says G is a branch of logarithm if and only if Gz equal to fz plus 2 pi ik.
Yes, sir.
If and only if. But a branch of logarithm is given here.
Yes,
Okay?
sir, but the value of k is ranging from in z or for some k or all.
I
So
think
this-
Suman, I
so
think
this is
Suman
what means.
is domain and k both are different.
The value of k is all z.
No,
Yes.
integers. Yes.
So it is for some in place of for some for all. It will be.
So what is meant by for all? If you make it for all, then you can choose any k, right? So this is not a single valued function then.
Okay,
If
sir.
you see
Yeah.
for all k, then this is not a single valued function. We are talking about a branch of logarithm, and a branch of logarithm is a well-defined single valued continuous function.
Okay, sir. Now I got, sir. Okay, thank
Yes,
you, sir.
yes.
After all, it is mentioned that GZ is a branch. So therefore, definitely it is for some k.
Yeah, a branch of logarithm. And the definition says that a branch of logarithm is always a single valued function. But nevertheless,
Yes,
since it is if and only if condition, the converse also holds. That means if you choose any k from z, then also, fz plus 2k pi I will give you
So
back a
therefore,
branch
the
of logarithm.
total family is fz plus 2k pi for where k is a parameter. This is the total family of them.
Yeah, that is what I said, right? That is what exactly I said. Nevertheless, so let us go to the converse. So that will be written as a remark. So you just look at the statement of the theorem, okay? What I am going to prove. So now the converse. Let be a branch of logarithm. The aim of this theorem, you just take a look at the statement of the theorem. Given a branch of the logarithm f in a region, so this is given. This is a part of the hypothesis, the first sentence. Then how can you obtain all branches of logarithm in that region G? That is the point. So if you have one branch of logarithm and if you just hold it fixed, this f, you can get all other branches of logarithm in the same region in terms of that branch of logarithm f. That is what the statement says. Okay? And this is the totality. This is the totality of the number of branches in the region G. Okay? So this is a part of hypothesis that we already have a branch of logarithm f in G. Okay? So let G be a branch of logarithm. Then we have both the conditions. Then G is continuous, and e to the zz is equal to z for all z in G. Okay. So we already have e to the fz equal to z, right? Because f is given to be a branch of logarithm in G. So, okay. And what happens if you have e to the something equal to e to the something? So if you just go back to the second class, this is the property of the exponential. You will see this
fz equal to dz plus 2k pi.
yes, fz is equal to gz plus 2k pi I. But this k will depend upon this z. This k depends upon this z, because here we are talking about two particular complex numbers, right? Fz and zz. These are two particular complex numbers. And for this, you obtain this k. If you change this z to be, say, z1, some other complex numbers, then this k will change. Okay, so this k will be a function of z primarily. Okay, let's see how it goes. So I just write two k pi I, where k depends on z. That is, you can write fz equal to gz plus, if it is a function of z, as I said, it depends upon z, so pi I. Okay? As k is a function of okay. Now we are going to show that this is actually a constant function. A single integer k will work here. How? Let us see. So you just look at this function kz. What is kz? That is 1 upon 2 pi I times fz minus zz, right? Okay. So therefore, this k, where does it define? This is defined from G to, this both functions f and g, they are defined on G. So this function is defined on G. And what is the right hand side? You just look at kj. This is an integer, right? This is an integer. So it is defined from G to C. And this function is continuous because f and g are continuous. And we have learned from the topological aspects that the continuous image of a connected set is connected. So G is given to be a region, so it is a connected set. So on the right hand side, its image will be connected. And what are the connected subsets of the set of integers? The singleton sets, right? So it has to be a constant. Okay. So this is continuous as f and g are continuous. Okay. So k of g is connected as G is connected Therefore, K of G is a singleton set. Okay. Therefore, Fz is equal to, sorry, Gz is equal to Fz plus 2m pi I. Okay. For some m belongs to z. So we see that if we have one branch of logarithm f, and if we add 2m pi I or 2k pi I for some integer k, then it is again a branch of logarithm in the same region. And these are the all branches of logarithm lies in that region. Okay, so this theorem tells us if you have one branch of logarithm, you can express all branches of logarithm in terms of that. That is what exactly this theorem tells us. Okay, like what we have seen in the previous example. If you just look at the previous example, this is exactly what we have done. We have one branch of logarithm here, which is the principal branch, provided our region is c minus the negative x-axis. Okay, then we have all branches of logarithm lying in that region in this way by adding 2k pi I. Okay, so, and this is a both-sided result, if and only if. So these are all the branches of logarithms. So just make a remark. So if f is a branch of logarithm, then the totality of are the functions. Okay. Now the point is that we just go back to our previous example, the principal logarithm. In order to define the principal logarithm, we have removed a half line from the complex plane. This half line is called a branch cut. Okay, in order to define a single valued logarithm, in order to define a branch of logarithm, we need to remove a half line. This half line is called a branch cut. So this half line is called
Sir, I have a question.
yes.
Sir, if we have e to the power z1 is equal to e to the power z2, then z1 is equal to z2 plus 2k pi I, right?
Yes.
That k doesn't depend on z1 or z2. Then why are we saying that this k depends on z?
Because here we are choosing functions. We are not choosing a particular point here. You just look at here we are defining a function. This z varies over all g. Whenever we are saying e to the fz equal to e to the zz, it holds for all z, right? It holds for all z. So for every particular z you have this. You choose a particular z, then e to the fz. Do you get my point? You are saying e to the z1 is equal to e to the z2. So this implies z1 equal to z2 plus 2k pi. I understand that.
Where
Okay.
k is in Z, right? Where k is in Z. And we don't
Yes,
say
yes, yes.
that.
For some k, for 1k, not for all k. Okay, for 1k. You guys are confusing all this. The thing is that it is for particular these 2 points. It is for particular these 2 points. Now, if I choose, if you choose one point, particular point from Z1, from G, okay, then
Okay.
you have FZ1 and GZ1,
Okay,
but
okay, I got it.
they are merely just 2 points, right? They are
Yes,
just
yes.
2 points. If you
Okay.
write e to the fz1 is equal to g e to the gz1, then this fz1 and gz1 they are just 2 points.
Okay,
And
got
corresponding to
it.
those 2 points, you have a particular k. But here, this z varies over all the domain. So for each point z, you have a k. Do you get my point? For
Yes, yes.
each point z, you have a k.
Okay.
Is it clear or is it not?
Yes, yes, it's clear. Thanks.
Yeah, please ask me if you have any other question.
Sir,
Yes.
sir, is there any other function other than logarithmic which satisfies the condition of branch of logarithmic?
So this is the reason it is called a branch of logarithm. Why do you search for other functions? If you have any other function, then there will be also a branch of logarithm, right? You just
Yes.
look at the name. It is called a branch of logarithm. If it satisfies, then it will be a branch of logarithm. If a function f satisfies this condition, okay, that is continuous and e to the fz equal to z, then it is a branch of logarithm. So it has to be, a branch of logarithm then.
So it has to be one of log functions.
No, no. It can be composition of these two. For example, you can think about log of some other functions like 1 plus 2y plus z squared. It is a composition of these two functions, log z and this function. This itself is a function, right? 1 plus 2y plus z squared.
Yeah,
So
but yes.
you can think about what are the branches of this function. I am going to at the end I will pose this question, and that is very easy to determine. That is very easy to determine. Once if you have the principal logarithm, okay. Once you learn the principal logarithm, then you learn everything. We will see that.
Okay, okay.
Okay. Yeah. So what have we learned until now? We have learned that in any region, if we have one branch of logarithm, then in terms of that branch, we can obtain all other branches of logarithm lying within that domain. And as a particular example, we have seen if we have the principal logarithm, which is defined on C minus this half line, okay, this is the domain, this is the region here, then we have all branches of logarithm in terms of this. Okay. Now, this is what is called a branch cut, as I said. You are removing one half line. You are removing one half line to define a branch of logarithm. This is called a branch cut for the principal logarithm. Okay. And for all branches of logarithm. Defined on Okay. Because we have seen that if we just add a 2k pi I with the principal branch of logarithm, with the principal logarithm, then it is continuous and it is a branch on the same region. We have seen that. So are all confusions clear? If the confusions are not clear, then I am not going to move. So I am, once again, I repeat, that argument. So you just see, this is very simple. We are writing e to the fz is equal to e to the gz, right? Where this f and g both are defined on g. Okay. So if we write e to the fz and is equal to e to the gz, then this z is a particular z. I'm not writing e to the fz. I'm not writing e to the fz is equal to, say, e to the gw. I'm not writing that. So for one particular z, if you call this z, if you choose a particular z, as I said, say you choose z equal to z1, this is fixed. Then if you write e to the f z1 is equal to e to the f z2, then they are merely 2 points, right? If you call them w1 and w2, if you call f z1 to be w1 and f z2 to be w2, then what does it give us? It gives us e to the w1 is equal to e to the w2. And we have that w1 is equal to w2 plus 2k pi I. Okay. So this is what we have. So if you change this point z1, then you have a different k. Then if you change this point from z1 to z2, okay, then what do you have? You have totally different k. Then you have e to the fz2 is equal to e to the gz2. So which is, say, e to the u1, e to the u2, where this u1 is fz2 and u2 is gz2. Then what can you say? u1 equal to u2 plus 2 m pi I for some m. And this m and this k, they are different because the points are changed, right? So they are different. So this is the reason k will vary. So if you talk about a function, then you have all points in this domain. So correspondingly, the k that you obtain will vary. And so this k will be dependent on particular z. Okay? So k will be a function of z. I guess now it is clear. Anyway.
Sir,
Yes.
if we consider points, suppose z and z plus 2k pi I, these two are different points.
Can you please repeat your question once again?
Suppose I have one point z naught, and
Z naught.
Yeah, if I take z naught plus 2k pi I,
Z naught plus 2k pi I, yes.
are they different?
Definitely
Yes,
they are different.
for non-zero k, they are different.
Definitely they are different. If you choose k to be non-zero, then definitely they are different, right? This is z naught and this is z naught plus 2k pi I. If this quantity is non-zero, then they are different points on the complex plane. If you choose your z naught to be, say, 2 plus 3i, okay, and then this point, what is this point? This point is z naught plus 2k pi I, which is equal to 2 plus 3i plus 2k pi I. And if this quantity is non-zero, meaning if k is non-zero, then definitely this is different, right? The imaginary part is different. This is 2 plus I times 3 plus 2k pi.
Yes. I'm sorry. My question was, do they give different value to e to the power z? No, right?
No. They give the same value. They give the same value.
So I'm confused there only. Like suppose we have e to the power z1 is equal to e to the power z2, then z1 is equal to z2 plus 2k pi I. So we get a solution set, right? So how can we say that we get just 1k?
Yeah, if you have e to the z naught and you have z naught plus 2k pi I. Okay.
Yes.
Now, if you change this point to z1, if you change this point to z1, my point is e to the z naught is equal to e to the z naught plus 2k pi I. That is fine.
Yes.
But if you change this point to z1, if you change this point to z1, then something else will get. What I'm talking is the following. Okay. Just look at here. You have e to the z1 is equal to e to the z2. Okay.
Okay.
So what does this imply? This implies z1 plus, sorry, z1 is equal to z2 plus 2k pi I for some k. You mind, for some k. This k is fixed. Once this z1 and z2 is fixed, this k is fixed. This k is a fixed integer. Why k is a fixed integer? Yes.
Sir, I think we can simply say that corresponding to every pair of complex numbers, we have an integer.
Okay. So just wait. Okay, just wait. Let me explain to her. So this implies k is, what is k? z1 minus z2 1 by 2 pi I. Am I correct?
Yes.
Am I correct? Yes.
Yes.
So this is one fixed complex number, one fixed integer, indeed. And this is particular, this is fixed. This is not a multi-valued thing. This is a fixed integer. Now the point is, if you change this point, z1 and z2, if you change this point, if you say e to the w1 and e to the w2, okay, then what can you say about w1? It is equal to w2 plus
2m pi I.
for some m, right? Now, what do you expect? You expect this m and this k, they are same?
No. Okay. Now I got it. No, they are not same.
Yeah, they are different.
Yes.
Because then m is equal to 1 upon 2 pi w1 minus w2. And this w1 minus w2 could be different from z1 minus z2.
Okay.
Yeah.
Yes. Thanks.
Yeah, no issue. So I'm sorry to interrupt. Someone else was saying something. So I had to interrupt because I was just explaining to her.
This is a good explanation, Sourav. I can say.
Yeah. So you were saying, Professor Allu, you were saying something?
No. Some other person is saying that for every pair of points Z1 and Z2, we have a unique K. But that is the explanation she is asking. So this is
that is the explanation. That is what I explained just, nothing else.
Yeah.
Anyway, I had to interrupt because I was explaining. So I'm sorry for that. Anyway,
I think it's a very nice explanation about branch cut and branch points.
Yes. So this is what is called a branch cut. Okay. So this is what is called a branch cut. Okay. And the thing is that now I am going to tell you, if until now we have only one example. Okay. So what example do we have? We have the example of this principal logarithm and the other branches of logarithm defined from this domain, okay, this region. Now the point is that, so here, if we talk about the principal logarithm, what is log z? You all know this is log mod z plus I times the principal argument, where this principal argument, okay. Now the point is that if you want to have your argument in between, some other interval of length 2 pi, for example, if you want to have your argument between 0 and 2 pi, this is also This is also a half open interval of length 2 pi. So if you restrict, if you think about your argument to lie in between this, then also this is a well-defined function from C to this, right? If you give it a name, say, say tilde. So you are considering this a function from 0 to pi, okay? Okay. Now, whatever argument you choose, it does not matter. Okay, we are interested about what are the values of argz. It's a multi-valued function. We have seen that this is argz plus 2k pi, right? So in terms of this function, we obtained all the values of the argument of z, all the values. Okay, for every particular z, on the right hand side, you have a set of points, right? Now the point is that if you choose your argument to lie in another interval of length 2 pi, then also you can obtain, then also, as I said, you can obtain the same set where k belongs to z. You can verify this. Eventually you have the same set. We are interested to find out what are the values. It is not a single valued function. Given z, non-zero, what are the values of argz? It's a multi-valued function. It has got infinitely many values. So all the values are obtained, in terms of this function, the principal argument, what we call. But instead of taking the principal argument, you can choose other arguments also. Okay, other sections of arguments. Once you fix the interval on the right hand side of length 2 pi, which is half open, you have this argument, to be a single valued and well-defined function, as I said. Now, if you fix this interval and restrict your argument in between 0 and 2 pi this way, and give it a name, like in case of minus pi and pi, we gave it a name, the principal argument, okay? Now here for this interval, I am calling it argument tilde, say. Just a name, it is just a notation, nothing else. Then also you can find out for given z non-zero, you can find out all values of argz in terms of this function also by adding 2k pi. The set here and the set here, if you vary your k over the integers, will give you the same set. Did you get my point? Now the point is that, so why don't you define logarithm in terms of this function? We have defined logarithm in terms of this function. Okay? If we want to define our log, if we define, say, we call it, say, log tilde z is equal to log mod z plus I arg tilde z, where arg tilde is this function, okay? Okay. Now this is again a single valued function. Am I correct? Do you all agree? This is a single valued function. Why single valued? Because this part is single valued and well defined, and this part is always single valued. So this is again a single valued function. Now please tell me when this single valued function is continuous. Like if we want to determine the continuity of the principal argument, we had to remove one half line. Here also, we shall see, we have to remove one half line. And what is that line? Who can tell me?
It will be positive real,
Right,
positive real axis.
Yes, that is the positive real axis. You see, so if you choose minus pi, okay, so you are taking this angle, okay, it does not touch there because minus pi is excluded. So all points on this part has angle plus pi because plus pi is included. And if you talk about this interval 0 and 2 pi, then you are choosing this half of the x-axis, right? So this is the point that has, if you choose a point here, it has angle 2 pi. Okay, this is the angle. So 0 is excluded, 2 pi is included. Sorry, it should be this way. So you are moving this way. Okay. So here, if you just look at any point on the right half of real axis, okay, you have a problem of continuity because 0 is excluded here. So if you want to have a continuous function, this function is defined everywhere on c minus 0, but it is not continuous. Once again, it is not continuous on this half line. So if you want to define a branch of logarithm, you have to remove this half then. Okay, so this is a branch of logarithm. So this guy is a branch of logarithm on you are just removing this half line. Okay, and you can, if you talk about this domain now, if you choose your g to be, if you choose your g tilde to be c minus 0 infinity, this region, then what are all the branches of logarithm? All branches of logarithm are nothing but this log tilde z plus 2k pi I, where k belongs to z. So this is the set of all branches of logarithm. Am I correct? Okay. In this domain, in this region, we are talking about this region. Okay. So this is the totality. This is the total set of, totality of all branches in G tilde. Now the point is that if you choose, I am just trying to explain. If you remove any half line passing through origin, okay, you can define a branch of logarithm there. So here we have removed this half line, the negative x-axis. Here we have removed the positive real half, and we have a branch of logarithm, and we have infinitely many branches of logarithm in terms of that, okay, by adding 2k pi I. Now the point is that if you remove any other half line, you have a branch of logarithm. For example, if you choose your argument to lie in between, say, minus pi by 2, minus pi by 2 plus 2 pi, okay, then which line you will remove? Can you please tell me?
Negative real.
Oh, sorry. Here,
Negative.
Negative imaginary.
you have to remove half line, right? So minus pi by 2.
Imaginary.
Minus pi by 2. You see the endpoints. You see the endpoints and try to locate it.
Lower imaginary.
So this is minus pi by 2. So this is this guy, right?
Of the OR.
So this line, this half line, you will remove this half line, right? Yes?
Yes, sir.
Yes, sir.
Yes, you will remove this half line. So here the branch cut is, what is the branch cut in the previous example? Here the branch cut is this guy. Here the branch cut is this line, this half line. Okay, so the branch cut. Here the branch cut is this. Okay. So, if you choose any other interval, you have one hop line to be removed. Okay. For example, if you choose pi by 4, then you are removing pi by 4 is this line. You are removing this hop line, then you are removing, this is your branch cut then. Okay. You just notice one thing, whenever you are removing one line, you are removing the half line whose one endpoint is 0 always. Have you noticed this? Have you noticed this? Here also, one half, one point was, say, 0 was included here. So this point, which is common to all branch cuts, okay, in a region, is called a branch point. So a point which is common to all branch cuts is called a branch point. So here 0 is a branch point, right? So in the above examples, 0 is a branch point. So is the idea clear? So what is a branch cut? A branch cut is that portion of a line that you are removing to have a branch of logarithm. Okay, as simple as that. And what is a branch point? That is common to all branch cuts. Okay, we are in a region. Okay, now if you specify your domain, for example, if you choose the unit disk of the complex plane, if you choose this to be your domain, okay, and if you want to define a branch of logarithm here, okay, then what would you do? What would you do? So this is your domain now. Okay. If you want to define a principal branch of logarithm, then you have to remove this line, right? This portion. Is that clear? If you want to have principal logarithm here, okay, then you have to remove this portion from the open disk. Okay, so this will be a branch cut then. Only this, including 0. So you guys are not responding. Are you understanding, all of you?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes,
Thank you. Thank you. So you have understood the notion of the concept of branch cut and branch point. What is a branch cut? The portion of the domain that you are removing to have a branch of logarithm there. Okay. Anyway, this domain contains the 0, so you have to remove the 0 first. Okay, because logarithm is not defined for 0, so you just remove the 0 first, and then you just look at If you want to have the principal branch of logarithm, then you remove this half line, this portion of the line, and you have the principal logarithm and corresponding all other branches. So what are the all branches? So they are just log z plus 2k pi I. Okay.
Sir, I had a question, sir.
Yeah.
Sir, log z plus 2k pi I, can it be geometrically viewed as the overlappings of this branch cut?
I did not understand. Overlapping
Sir,
means?
Overlapping means 2k pi I argument variation is coming, no? So one rotation, does it mean like that, sir?
If you change k, okay, you
Yeah.
have a new function.
Yes, sir.
If you change k, you have a new function.
No, I'm asking the geometrical viewpoint, sir.
So how do
can we
you
visualize? Yeah, how can we visualize this other branch cut? That's my question, sir.
No, the branch cut is same here. If you choose log z, the principal logarithm, the branch cut is this guy.
Okay.
Okay.
Yeah.
If you choose log z plus 2k pi I, then also the branch cut is the same line. Because you just look at log z is continuous everywhere other than this line, this portion,
Yes,
including
yes,
0.
Yes.
So this is also continuous everywhere other than this portion because you are adding just a constant. So this does not change continuity, right? Okay.
Yes, sir. Yes, sir.
Yeah. So with respect to this branch cut, these are all branches of logarithm. That is the point. These are all branches of logarithm with respect to this branch cut. Okay.
Okay.
Yeah, that is the point.
Okay, okay, sir. Okay, sir.
The branch cut is a single branch cut, and it gives you all these branches of logarithm. As simple as that.
Okay, sir. Thank you, sir.
Yeah.
Sir, I have a question, sir.
Yeah, please.
Sir, I want to know the branch point is dependent upon what? Is it dependent upon the logarithmic function or what?
No, it's not dependent upon the function. You see, here you have one branch cut and you have all these branches, right? And as I said, if you remove another line, another radial line, okay? For example, if you remove this line, you have another set of branches of logarithm, okay? You have another set of branches of logarithm. Do you get me?
Yes, sir.
But the point is that, so this is also a branch cut. This is also a branch cut for other branches of logarithm, not for these branches, definitely, for other branches. Okay?
Yes, sir.
Now, what is common here is this point, origin, you see. That is the point that is common to all branch cuts. Okay?
Yes, sir.
This is what is called a branch point. Okay, now I am moving to the power, the complex power. So hold a second. Now, so I just give you this question, what you should discuss among yourself in the tutorial session and think about it. So, how would you make a branch cut? To define a single valued branch of the function log of z plus I minus 1. So you see, this is a composition of two functions. Okay, if you call this function to be fz, if you call fz to be z plus I minus 1, then this is a composition of these two, the logarithm and the function f. Okay, nevertheless, you just think about it. Okay, you just think about it. So the point is that the algorithm is same. Okay, the algorithm is same. Whatever I have shown you until now is about this guy log z, where this function fz equal to z here. We are dealing with this particular function fz is equal to z. Do you get me? Now, if you change this function, fz to be say z plus I minus 1, meaning z plus some constant. This is again a nice function, no doubt about this. Now, how can you find out branch cuts? You just find out one branch cut, that suffices. Let's see. Okay, so this is a question that I just leave with you, and you can easily do. If you have followed this lecture, then you can easily do it. This is what I believe. So let us move to power functions.
Sir?
Yes.
Sir, for every multi-valued function, we can have a branch point and branch cut, etc.
Yes,
so
yes, exactly.
So is it necessary that for every multi-valued function, we have a single branch point?
No, the thing is, no, not necessarily. The thing is that whenever you talk about multi-valued function, and if you want to get a single valued function, actually, I cannot talk about analyticity. That is the problem. It is not yet introduced. The thing is that what is a branch of a multi-valued function? A branch of a multi-valued function is a single valued function which is analytic, and you choose the domain accordingly and maximize it. What is the maximal region or domain where you can have an analytic branch, an analytic part of the multi-valued function. Okay. Anyway, the next speaker will definitely talk about this. He will define differentiability and analyticity, and he will talk about analyticity of branches of logarithm. Okay, so he will definitely talk about this. Don't worry. So,
okay, sir. Thank you.
Sir,
so yes.
What is Riemann surface where log becomes single-valued functions?
So the next speaker will say that. Next speaker, you please be, you just please wait for some time. The next speaker will tell you in detail. He's supposed to discuss everything about Riemann surface and all possible branches of logarithm and everything. Okay.
We are going a systematic way of completing the.
Yes. So the next speaker will explain all this. So
Sir, I have one question here, sir.
Yes, please.
Sir, does this definition remain same? The definition of a branch of a function, I mean that very e power fz must be z. For example, if we choose the nth root of a complex number as a multiple valued function, sir, what's that time the definition of branch of that function?
So that is what
same?
I'm going to say. That is what I'm going to tell you. Okay.
Okay,
just bear with us.
Thank you,
so
sir.
Let alpha be a complex numbers. Okay. So we define the power function z to the alpha to be the multi-valued function how do we define it? Z to the alpha is equal to exponential alpha log definitely whenever you talk about log z, you say z is non-zero. Then If we define this way, it is a definitely multivalued function because log z is involved here, and it has we have seen a lot of branches. So accordingly, we can talk about the branches of z to the alpha. Okay. So what are the values? The values of z to the alpha as a function. The values of z to the alpha are given by z to the alpha is equal to e to the alpha. You have log mod z plus I times the principal argument plus 2k pi I, okay, where this key runs over integers. So these are all the values definitely without any hesitation. So this is precisely e to the alpha log z times e to the two k pi alpha I. Okay. So see, how do we obtain all the values of z to the alpha? We are obtaining all the values of z to the alpha by multiplying this guy e to the alpha log z by this quantity. Right. Now the point is that when alpha is an integer, if alpha is a positive integer, say for example, if alpha is 0, then it is just z to the alpha is just e to the alpha log z, and it is single valued. Okay, and what is that? What is that? That is just 1, right? That is 0, and that is 1. Okay. And now the point is, if it is a positive integer, if alpha is a positive integer, say if alpha is equal to n, then what do you have? What do you have? E to the, I'm talking about this part, okay? E to the 2k pi alpha I. What is that? This is equal to 1. Do you agree with this? If alpha is equal to n, okay? And accordingly, you have z to the alpha to be equal to e to the alpha log z, or better to say, I put n here. And what is that? What is the right hand side? What is the right hand side? How many values does it have?
1, sir, 1.
Yeah, so what are the values of this? How many values, how many values of z to the alpha does it have? Only 1, right? Only 1 value. So this is single valued. So this is our usual power, z to the n. What we know, what we all know, the polynomial z to the n. It is single valued and well defined. Now, if we have alpha to be 1 upon n. Oh, sorry. Here, I should have said z. I think I should have said z here. Yes. No, then, okay, wait. Okay, so here we let us deal with the positive integer so that we can get a regular polynomial. And if alpha is 1 upon n, then what happens? Then what can you say about 2k pi alpha I? You see, so this is e to the 2 pi by n I to the k, right? Now you see, when k is a multiple of n, you have this quantity to be equal to 1. And what are you having on the left hand side? Left hand side you have z to the 1 upon n. Okay? And on the right hand side you have this guy log z times e to the 2 pi by n I to the k. Now, how many values, how many different values does this part have when k rounds over integers?
N, sir. N.
N values.
You will have precisely n values. So it has, n values. And we have learned this. I gave it as a question in the assignment. So this is what is called nth root of z. Nth root of z. And there are precisely n number of nth root of z. And this happens for every complex number, right? What are alpha to the 1 upon n? If w is equal to alpha to the 1 upon n, if z equal to alpha to the 1 upon n, then this z is a root of z to the n minus alpha equal to 0. And the left hand side is a polynomial of degree n. And from the fundamental theorem of algebra, we have learned it has precisely n values. Now that problem of assignment, it tells us what are those exact values. It gives you an algorithm to calculate, nevertheless. So these are the power functions z to the n and z to the 1 upon n. So I am going to briefly describe what are the trigonometric and hyperbolic functions. They are very easy. So I have just kept them written. So you see, we know this, e to the I theta equal to cos theta plus I sin theta. We all know this. And show is e to the minus I theta. Show that we have cos theta and sin theta in terms of the exponential function in this way. So this is defined for real theta. Okay. Now the point is that this gives us motivation to go beyond the real line and go to the entire complex plane. Let us define cos z and sin z this way in the similar fashion, so that it agrees with our definition in the real line, whatever we have learned in real analysis. Okay, it agrees with that. If you put z equal to x or some real number x, you will see it coincides with whatever we knew earlier. So we have, if we define complex, cosine and sine this way for all complex numbers, they have these properties. I have written down them. It's 2 pi periodic. So similarly, one can define hyperbolic functions for all complex numbers in a similar fashion. You just look at here. Okay. Now the point is that then also we have a set of properties of the hyperbolic functions. It's 2 pi I periodic. Okay. And there is an interplay between the hyperbolic functions, sine hyperbolic and sine z, cos hyperbolic and cos z, and they can be easily deduced. This is just school level algebra, nothing else. Now, what is important here is the zeros of the sine z. Let us see what are the zeros. We know for the real sine, when sine is defined on the real line, we know what are the zeros. They are just n pi, right? Where n varies over the integers. Okay. Now, how can we determine the zeros of sine z when z runs over the entire complex plane? What are the zeros of sine z? So that is what is precisely done here. You will see this equality, sine z square equal to sine square x plus sine hyperbolic square y, where this z equal to x plus iy. Okay, where z equal to x plus iy. Okay, we have this. Okay, so from this, you just look at the right hand side. When sine z is 0, sine z is 0 if and only sin x is 0 and sin hyperbolic y is 0. And the zero set of sin x and sin hyperbolic y, when x and y are real, they come from the real line, we all know they are just n pi. This is the entire set. So the zero set of sin z, when z comes from the complex plane, is also the zero set of the real sin x, the same set of zeros, right? So the zeros of sin z, they lie on the real line and they are of this form in z, n pi. So similarly, you can determine the zeros of cos z. They will be equal to the zeros of cos x, indeed. Okay. Now you can think about the set of zeros for sin hyperbolic z and cos hyperbolic z. Please determine them. And the other trigonometric and hyperbolic functions can also be defined using this formula. Of course, whenever you talk about tan z to be equal to sin z upon cos z, you have to be careful to make the denominator non-zero. Okay, you have to define it properly. Okay, so you can you can verify that there is an interplay between tan z and tan hyperbolic z. It's precisely this is given by this. Okay. Now, if you talk about the inverse trigonometric and inverse hyperbolic function, they are multivalued functions. Definitely they are multivalued, right? Because if you have w is equal to sin inverse z, for example, you assume we are going to, it's an algorithm. Let us determine what are the values. Then you have sin w, and by formula sin w is this guy. This is equal to z. And accordingly, we have this equation. Okay. This is a quadratic equation where the variable is e to the iw. So it has precisely two values, which is obtained this way. Now, if you take logarithm, you hit both sides by logarithm, then you have this. The value of sin inverse z is precisely log of minus I times log of this guy. And what is that? What is that? It's a multivalued function. Since log is there, again, it's a composition of two functions, log of something where what is inside is also a function. Okay. So now the point is, how can you define a single valued sin inverse z? So it depends upon what branch you are choosing. You just find out what are the branch cuts, at least for once. Okay. You just try to find out one branch cut in terms of the principal logarithm. If you choose to have the principal logarithm of this, what are the branch cuts? You have to remove two hop lines. Just believe me. I have just written here, but you just verify this, right? You have to remove these two hop lines to have the principal logarithm. And then you can say that the sin inverse z is a well-defined single-valued continuous function. Okay, and you can do the same thing for cos inverse z and sin hyperbolic inverse z and cos hyperbolic inverse z. Okay, so there are some interplays between the logarithmic function and the exponential function. For example, there are some basic properties what we have learned in school, like if you choose the real line, what is the image of under the exponential function? The exponential function, if you think about any line, okay, parallel to x-axis, then it will be mapped to a half ray. We all know this, right? And similarly, if you have a line parallel to y-axis, it will be a circle. So these are all basic and elementary things what we have learned in school. Now the point is that if you talk about the logarithmic function, at least for a branch, then it is a single valued function and it will return you. It's a reverse procedure. So it will map that half ray back to the line parallel to the x-axis. So I will, when I post this note, I will just briefly write them down with example and I will post the note. Okay. So I just stop here because the next speaker will start from 4 o'clock, I guess. So I just stop my lecture here. And there will be several further rounds of discussion. I'm just, I stopped sharing. And there will be several rounds of discussions of logarithm. Once again, its analyticity by the next speaker. Don't worry. Okay, don't worry. It's a complete course, as Professor Vasudev Rao already shared. It's a complete course, and nothing will be, nothing will be dropped. Just believe me, nothing will be dropped. Everything will be covered up. Okay, so I stop here.
Thank you, Dr. Sourav. You have given a beautiful introduction in the 4 lectures.